Hello and happy election day. Welcome to the lesson on the Krebs cycle, also known as the citric acid cycle. Krebs was the guy that discovered or did most of the research on the citric acid cycle. And in this lesson, we're going to go through sort of what happens in the Krebs cycle. So the goal of this cycle is to get the rest of the electrons that are stored in pyruvate. So if you remember, basically pyruvate is basically half a glucose molecule, and our goal is to get, in the Krebs cycle, is to get the rest of the electrons that are stored in pyruvate into NADH. Okay, so that's sort of the goal of the cycle, is the rest of the electrons that are stored in the 2-pyruvate that are made at the end of glycolysis. Okay, our goal is to get the rest of the electrons out of them and into NADH. And now we're going to see how that's done. So before we begin the cycle, there's sort of what I call the bridge to the Krebs cycle, or the citric acid cycle, where we have to take the pyruvate and convert it into a molecule known as acetyl-CoA. So let me get my pen out. So this is pyruvate, right? And it's half a glucose molecule with some hydrogens removed or electrons removed. Because if you remember, glucose has six carbons, and pyruvate has 3. So this is essentially what half a glucose molecule with some of the hydrogens removes. And before we enter the citric acid cycle, we are going to turn pyruvate into a molecule called acetyl-CoA. And one of the steps that we're going to do is we're going to remove basically a carbon dioxide from the molecule. So you can sort of see, so carbon dioxide is CO2, hopefully you know that. And one of the steps, and we're going to see the complete process in a second, is to remove carbon dioxide from the molecule. And then we're going to produce acetyl-CoA. So here is pyruvate, which is made in the cytoplasm, and it was made in glycolysis, and it has to enter the mitochondria. So that's sort of the first thing that has to happen. Is the pyruvates, 2 of them, from the glycolysis need to enter the mitochondria. Then 3 things happen to pyruvate. It loses a carbon dioxide, which I showed you on the previous slide, and a hydrogen is taken from it. So that's an electron. So NADH, NAD grabs a hydrogen from the pyruvate. And then last but not least, something called coenzyme A is added. Okay? And it doesn't matter what coenzyme A is, just that it helps all you really know is that it helps with acetyl-CoA, or it helps acetyl-CoA enter the Krebs cycle. So again, there are 3 things. Remove O2, take an electron, which that turns NAD into NADH, and then add coenzyme A. So those are the 3 steps in which I call the bridge to the Krebs cycle. So here, once again, we see the steps again. We have pyruvate. We remove a carboxyl group, which is essentially carbon dioxide. We take an electron, making NADH. So our products that we have NADH, we have CO2. And then we add coenzyme A to make acetyl-CoA. Now you have to remember that this happens twice, because there are 2 pyruvates. So at the end you have 2 NADHs, 2 carbon dioxides, and 2 acetyl-CoAs, and because 2 pyruvates went through this bridge. So now we're ready for the citric acid cycle, and the citric acid cycle takes place in the matrix of the mitochondria. So if you remember the mitochondria, here we have our mitochondria, then we have a little cristae bends in the inner membrane, and then here inside, this here is the matrix. And it's important to remember that the matrix contains lots of enzymes, because each step in the Krebs cycle is catalyzed by a different enzyme. And again, the point of the Krebs cycle is acetyl-CoA is going to enter the Krebs cycle, and we need to take the rest of the hydrogens out of our electrons. Really, when you're taking, you're really taking the electrons, and the hydrogens just hop on. Our goal is to take the rest of the electrons that are in acetyl-CoA, and we also remove the carbons by removing carbon dioxide. So the fancy way of saying what's the purpose of the Krebs cycle is to complete the oxidation of acetyl-CoA to carbon dioxide. That's our goal, is to completely oxidize acetyl-CoA to carbon dioxide by taking all of its electrons. Okay, and the molecules that take the electrons are NADH, and another molecule called FADH, which is similar to NADH. It just has a different structure. It's needed to be that structure for the enzyme to function. We're not going to go into its structure. Okay, so the citric acid cycle has 8 steps, and each of the 8 steps, okay, is catalyzed by its own specific enzyme. The first step, okay, which we're going to look at in a second, is when acetyl-CoA joins with a molecule called oxaloacetate to create a molecule called citrate. Okay, we're going to look at this in a second. Then the job of the next 7 steps, which we're not going to look at in that much detail, okay, basically what they do is they remove carbon dioxide and take electrons and give them to NADH and NADH2. At the end of the cycle, okay, you've removed all the carbons, okay, that were left in acetyl-CoA, and if you look at acetyl-CoA has 2 carbons. All the carbons are in carbon dioxide, and you have taken all of the electrons that were originally in glucose, then were in pyruvate, and then were in acetyl-CoA, and now they're either stored in NADH or FADH, and we'll sort of see how this happens in the cycle. We're going to look now at the cycle, but remember the goal, and I want you to write this down, so if you need to pause and replay me back, okay, the goal is to take all of the electrons that are left in acetyl-CoA and store them in NADH or FADH2. And when we do that, okay, we remove carbon dioxide from the molecule. So we have acetyl-CoA, which I'm going to abbreviate A. Okay, our goal, okay, is to take all the electrons that are stored out of them, okay, and then at the end, we're left with these molecules of carbon dioxide, okay? And you can obviously write out acetyl-CoA. These electrons are stored in the molecules of NADH, which it takes a long time to write. And I'm going to pause it while I write FADH2 to save time. So again, the goal is to take the electrons that are left in acetyl-CoA and store them into NADH and FADH. This should be a 2. Sorry, I'm at home, so don't have this more work. All right, we're going to take a look at the cycle. You're not going to have to remember the steps of the cycle. We're going to take a look at it. So this is the cycle. We add acetyl-CoA enters the cycle, remember from the bridge part, and it joins with a molecule called oxaloacetate. Okay, it loses coenzyme A, and that forms the molecule citrate. Then there's a rearrangement of the molecules by removing carbon dioxide, removing water, and then re-adding it to form from citrate to form isocitrate. Okay. Then in the third step, okay, we remove carbon dioxide and we take an electron, making NADH. Okay. Okay. Then we have this molecule. Who cares what its name is? In step 4, we remove another carbon dioxide, re-add coenzyme A, and do another oxidation or take another electron from whatever molecule this is or what it is in the cycle. Okay. Now here, coenzyme A is removed. Okay, and this molecule is unstable, so we can add a phosphate group. Okay, and then actually remove it and then add it to ATP by substrate level phosphorylation. I'm not going to go into the details. This step here is so complicated, and if you ever take biochemistry, you sort of need to go into all sort of like the rearrangements that happen. But again, this arrangement makes an unstable molecule, which really wants to get rid of the phosphate group, and that allows us to make ATP by substrate level phosphorylation. Okay. Then we have this molecule called succinate, and by no means need to remember any of these molecules. And we oxidize it again, but this time instead of NADH, the molecule that takes the electron is FAD, which turns it into FADH2, and we make the molecule fermate. Okay. Then we add a water, and that sort of allows for a reorganization of the molecule. We do another oxidation, take an electron, and we get NADH, and then we reform oxalate, which re-enters the cycle. Okay, but what's the point? At this point now, all the carbons that were in glucose are now in carbon dioxide. Remember, we did that earlier also in the, remember this happens twice, so every molecule you're getting 2 of them, so you're getting a total of 4 carbon dioxides from this cycle because you're doing it twice. So that's the first point, is that all the carbons in glucose are now in carbon dioxide. We got 1 in the glycolysis. I'm sorry, we got 2 in glycolysis. 1 in glycolysis, 2 in the bridge, and then 2 in glycolysis, 2 in the bridge, and then 4 in the Krebs cycle. I'm losing track of my numbers. And then all of the electrons in glucose are now in NADH or FADH2. Okay? And I'm going to look at the numbers later, but for now, that's fine. This is the summary of the Krebs cycle. And again, I sort of want to focus on what we get out. So this is per 1 acetyl-CoA. So per 1 acetyl-CoA, you get 2 CO2 out, 3 NADH, 1 ATP, and 1 FADH2. And again, every step in this cycle, this is really sort of what you need to know. You don't need to know all those other molecules. But it is important to know that every step in this process, which is an 8-step process, is catalyzed by its own enzyme. So if one of those enzymes is not working Houston, we have a problem, just like Houston did in the World Series. And again, because there are 2 acetyl-CoAs, all right, because there are 2 acetyl-CoAs, the total that you get in the end, all these numbers, you really get out 4 carbon dioxides, 6 NADHs, 4 ATPs by substrate level phosphorylation, and 2 FADH2s. So because you have 2 molecules of acetyl-CoA from pyruvate and then from glucose originally. So here we're going to summarize what we've made so far. So in glycolysis, which happens in the cytoplasm, we oxidize glucose, okay? And glucose, if this would work, hold on. So I got cut off, so I have to repeat what I said. So we have glucose, and then we oxidize glucose, and we get the hydrogens and electrons from glucose into a 2-acetyl-CoA, and it also gets split in half into 2-pyruvate. And the red molecules are the ones that have carbons in it. So in glycolysis, we basically done an oxidation and split glucose into 2-pyruvate. Now in the bridge to the Krebs cycle, we take pyruvate enters the bridge to the Krebs cycle, and we oxidize it and get out 2 NADH, and we produce 2 carbon dioxides, and we're left with 2 acetyl-CoA. It's important to remember that in glycolysis, as I get my pen out, we had 6 molecules of carbon, which are now in pyruvate, which has 3 molecules of carbon, and then are in acetyl-CoA, which has 2 carbon molecules. So in the bridge to the Krebs cycle, we oxidize pyruvate, getting out 2 NADHs. So the electrons from pyruvate are now in NADH. We have 2 carbon dioxides, and what's left of glucose is acetyl-CoA. Then acetyl-CoA enters the Krebs cycle. Okay? And we went through the Krebs cycle in some detail, and you don't really need to know the details, but we completely oxidize acetyl-CoA into 6 NADHs, 2 FAD2s, and 4 carbon dioxides. Now, what's the point? Okay, the point is that the 6 carbons, okay, are now in the carbon dioxides, okay, and the 12 hydrogens, which really are electrons, are in the NADHs, so 2, 4, 10, 12, so all the hydrogens, or all the electrons that glucose originally, okay, are now in NADH and FADH2. Okay, now where are NADH and NADH going to do? We're going to use those, okay, electrons in the electron transport chain, which we're going to learn tomorrow, okay, to make ATP by a process known as oxidative phosphorylation, okay, which is my favorite process in the entire universe. So these NADHs, the electrons in NADH and FADH2, are going to be used to make the rest of the ATP that we need by oxidative phosphorylation, which we will see tomorrow. Answer the guided questions. Have a good day.